Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about analysis of recursive functions. So let's get started. So far we have discussed how to analyze iterative solutions, and in iterative solution what we did, we simply count the number of operations in the program and we say that okay, the order of growth of this function is going to be a theta n or theta 1 or theta log n. But this becomes challenging when we consider recursive solution, because if you look at this program, this is a recursive program, and what it does, it's simply calling itself by reducing the input size by 1. So if you observe this code closely, we do not have any loop sort of structure here. We have a simple print statement here and a function that is calling itself. So this is a real challenge in recursive solution, that we do not have loop like structure and the function is calling itself. So here it becomes really tricky to find the order of growth of this function or the time taken by this function to solve a problem, right? So now the question is how to find order of growth of a recursive function. So this is where recurrence relation come into picture. So what we do basically, we just write the recurrence relation of a particular problem and then we try to solve that problem using recursive tree method, right? So what we do in this video we will learn how to write a recurrence relation of a problem, and in second video we will learn how to solve that recurrence relation using recursive tree method. Alright, let's move on to our first example. You can see this piece of code, and this is a recursive code. So to write the recurrence relation, we first need to find the amount of work we are doing in this function. So if you look at this function closely, in the first line we are doing some constant amount of work. See, here we are just checking n equal to 0 and we are returning. It means we are simply doing constant amount of work. So we can write constant, or we can also write theta 1 work. In second line we are simply printing the value of n. So this is also a constant amount of work, right? So whatever work that doesn't depend upon the input, we call it a constant work. So in this function, line 1 and line 2 both are doing constant amount of work. Now let's move on to third line. The third line is function itself, and this function is calling itself by reducing the input size by 1. So if we want to know that what amount of work this third line is doing, so we can write that this line is doing theta n minus 1 amount of work. See, these are recursive function. So we can write theta of n minus 1, and theta of n minus 1 is again going to call theta n minus 1 minus 1. That's why. Okay, so far so clear. Now let's see how to write the recurrence relation. So just like we represent function as f, similarly we represent the time taken by function as t. So we can write like this. Let's say time taken by our input n is equal to time taken by n minus 1 plus constant. So this function is taking how much time? It is taking constant time just to print this line, and it is taking n minus 1 time. So that's why we are writing here time taken by our input n is equal to time taken by n minus 1 plus constant. And this is true when our n is greater than 0. So this piece of code only execute when our n is greater than 0, right? So what happens when our n becomes 0? So the relation for n equal to 0 comes out to be when our n becomes 0, the time taken by this function is going to be constant. And we can see here when n becomes 0, we are just doing constant work, right? Now this is our recurrence relation of this example, and we can solve this using recursive tree method, and we will see it in the next video. Okay, cool. Now let's move on to our next example. So in this example, so let's find out how much work we are doing in this function. So the first line is a constant operation, second line is also a constant operation, and the third and fourth line we can write it as a theta n minus 1 plus n minus 1, because this function is doing n minus 1 amount of work in the third line and again the n minus 1 amount of work in the fourth line. So we can write it like this. Okay, now let's write the recurrence relation of this function. So the recurrence relation of this function comes out to be the time taken by this function when our input is n is equal to time taken by this function n minus 1 plus time taken by again this function n minus 1 plus constant. And we can rewrite this relation like t of n is equal to 2t n minus 1 plus c. So it's going to be time taken by our function when input is equal to n is equal to 2t n minus 1 plus c, and this is the time taken when our n is greater than 0. And what about if our n is equal to 0? So when our n equal to 0, the time taken of this function is going to be constant, because when n becomes 0, we are just simply doing constant operation here. Okay, all right, let's move on to our next example. So in this example, let's find out the amount of work we are doing. In first line, we are doing constant amount of work. In second line, we are doing constant amount of work. And in third line, amount of work we are doing is theta n by 2, right? Now, how to write the relation, recurrence relation? We can simply write the amount of time taken by this function is going to be t n by 2 plus c. And this is the amount of work we are doing when n is greater than 1. And what happens when n becomes 1? The amount of time this function takes is equal to constant. Same as previous example, in first line when n becomes 1, we are just returning. So we are doing only constant amount of work here. Okay, great. Let's move on to the next example. Now let's see this example. In the first line, we are doing constant operation. In second line, we are also doing constant operation. In third and fourth line, the amount of work this function is doing is n by 2 and n by 2. Okay. Now, how to write the recurrence relation for this function? We can write it like time taken by this function for input n is equal to time taken by function n by 2 plus time taken by function n by 2 plus constant, right? And this is happen when n is greater than 1, right? And what when n equal to 0? The amount of time taken by this function is going to be constant, because when n becomes 1, we are just returning, and it is a constant operation. Great. Now let's move on to next example. So in this example, in first line we are doing constant operation. In second line, now we are not doing any constant operation. Instead, we are doing linear operation, because we are running a loop from 0 to n, and in each iteration we are printing the value of n. So the amount of time taken to run this loop is going to be theta of n. It is the exact bound. Exactly, we are running this loop for n times. And in the last line, the amount of work we are doing is theta of n by 2 and theta of n by 2. So let's write the recurrence relation of this function. So it's going to be the time taken by our function when input is n is equal to time taken by the recursive function, and the input to that function is going to be n by 2 plus the time taken by the recursive function plus the constant. And this is when n is greater than 1. And when n is equal to 1, the time taken by this function is going to be constant. Okay, so far so clear. Let's see the next example. In this example, in first line we are doing constant operation. In second line we are just printing, so it is also constant operation. In third and fourth line we are calling this function with n minus 1. So the amount of work we are doing here is theta of n minus 1 plus theta of n minus 2, right? See here, the recursive function is calling with the different inputs, not the same inputs. In first function we are reducing n by 1, and in second function we are reducing n by 2, right? So let's write the recurrence relation of this function. It's going to be time taken by this function when our input is n is equal to time taken by the internal recursive function, that is n minus 1, plus the time taken by internal recursive function when input becomes n minus 2 plus c. This is the relation when n is greater than 0, and when n becomes 0, the relation is going to be time taken by this function when n is equal to 0 is equal to constant, right? Because we are performing constant operation when n tends to 0. So in this video we have seen that how to write the recurrence relation of the functions, or I could say recursive functions. In the next video we will see how to solve this recurrence relation and to figure out the order of growth of time taken by these functions. So I hope now you have a clear understanding about how to find the recurrence relation of a recursive function and how to find the amount of work our recursive function is doing. So this is it for this video. Thanks for watching. See you in the next video.